Hi, my name is Kei Han, and this is my software architecture project presentation about search engine web app. This is a Spring project that implements a search engine as a web app using Java. The project includes web crawling, URL classification, specific page information acquisition, term frequency generation, file downloading, and most importantly, search function. The operational scenario of this project is when users want to look for specific information among text pages, including TXT, PHP, HTML, HTM, net pages inside the target website. They can get results that are most related by inputting the domain of the website, number of maximum search pages, and search keyword. Users can also download analytic files generated during the search process. Some rules of the search engine. Searching won't go outside the target website. Searching uses BFS strategy and number of pages reached during the searching process won't exceed the maximum numbers that users indicated. Searching keywords will be expanded according to the thesaurus. There are two architecture options for this project. The first option is posted here, pipe and filter style. So here is the component diagram of pipe and filter architecture. You can clearly see the structure of this architecture. The procedure core connectors are controlling the flow of data. In the beginning, the user is asked to input URL, number of maximum search page, and search keyword. For the left part, web page crawler will receive the URL and number of maximum search pages and return a set of URLs. In the URL classification component, all the URLs will be identified to different classes like broken pages, non-text pages, pages outside, duplicate pages, pages not allowed to crawl, and text pages. And we'll generate a file of this classification for later downloading. Then the page information generation component will collect base information of these pages like URL, title, fragment, which is a small part of the page content, size, and modification date. And we'll generate an Excel file to store this information for further downloading. Text content extraction component will also get the URLs for the text pages. It will extract all text content on the page and send it to word steaming component. Word steaming component will steam each word and storing them to a dictionary. Steaming is the process of producing morphological variants of a root word. For example, it will convert like, likely, liking, liked to like, which is the root word of these four words. Term frequency matrix generation component will get the dictionary and make it a matrix that will act as an important role in the search process. On the right part, search sentence will be sent to query normalization component, which splits the sentence and steams each word. The thesaurus expansion component will expand the search sentence. This thesaurus contains a list of words with their synonyms. What the thesaurus expansion do is that it adds the synonyms of a word to the search sequence. For example, if the original search sequence contains photo, it will be added with photograph, image, and picture. Along with the matrix generated before, pages will be scored and top related pages will be shown. This is a class diagram of pipe and filter style design and the mapping from classes to component and connectors. The pros of the pipe and filter style is shown below. The first one is that this architecture makes the project easier to maintain. We can simply add new filters for further requirement. It is also easier to debug. We can simply check the input and output of each component to locate the problem if something goes wrong. The last one is that it doesn't require extra storage space. The con of this architecture is that it may take more time for each search, since there won't be any cache and it is executed single-threaded. The second option is Blackboard architecture, and here is the component diagram. We can see that the components Blackboard architecture has is like what Python filter architecture have. The difference is that each component will have to execute read and write operation on the Blackboard, which is the database in this project, through the data access connector. We can have a detailed view of these four components on the left. The user input component provides URL, number of maximum search page, and search sequence to the Blackboard. Then the web page crawler obtains the URL and maximum number of search page and provides a set of URLs of all the search pages to the Blackboard. The URL classification component gets the set of URLs and returns the URLs of text pages. Lastly, the page information generation component obtains the set of URLs of text pages from database and will generate an Excel file containing all the information of these pages. Here is the class diagram of Blackboard style design. We can kind of see that almost every component have set function and get function. And this is the mapping from classes to component and connectors. The pros of the Blackboard style is that components are working individually without affecting others, which leads to an easier module design. And the cons for the Blackboard style is that it needs extra storage space, especially when it receives a large number of search requests. And frequent database read and write operations will lead to worse performance of the system. I believe Python filter style is more suitable for this project. Firstly, Python filter style provides an explicit display of the overall process of the system, allowing me to monitor the input and output of each procedure, making it easier to debug and add new filters for additional features. Secondly, it has much less database operations comparing to Blackboard style, improving the performance of the system. And for further extension of this project to next level, which is deploying on the server and allowing public access, store result and data generated during each search can be extremely expensive for the Blackboard style. This is a screenshot of successful compilation and execution. Next, I'm going to show how the search engine works. So this is the home page of the search engine. You can see you have to enter URL, maximum number of pages, and the search keyword here. And there's a suggest search listed here. So let's input the URL and set the maximum number to 10 and search for golf. It may take a few seconds. So we can see the search result on this page. It is searched in 6 documents and the Steam dictionary has 149 words, which means there are 6 pages in is text page among the total 10 pages. And there are 149 words in the Steam dictionary. So let's go back and set the maximum page to 100 and click search. It will definitely take more time than the previous search because the maximum search page is 10 times of the previous time. We can see the results here. It got some matched pages. It is searched in 42 documents, and the Steam dictionary has 1083 words. There are 4 documents that match the golf word, and it is displaying the 4 top matches. So we can see all the results have an URL and the score and the snippet. The snippet is the first 20 words of the content on the page. So we can see this URL have the highest score, which is 0.6, which means it is the most related page of the World Golf. And you can click the link here to view the content of the page. Let's go back and search for another word, CS. So the word CS is expanded as CS and computer science according to the thesaurus. It may take a few seconds for the result to show because we still set it 100 pages. So we can see the results here. There are 3 matches to CS and computer science. We can also download the files we mentioned before here. So here you can download URL classification, download page information file, and download term frequency matrix. Let's check what's inside the downloaded files. So for the URL classification file, you got a few classes of the URLs like pages in the site, pages out of the site, pages not text file, pages broken, pages duplicate, pages indexed. For the page information file, you got a list of URLs and their title. If they don't have title, that will be empty here, and the modification date and the size. So this is a term frequency matrix document. There's a list of documents and a dictionary of all the themed words. So we can see here, if it shows 5, it means this word is shown 5 times in this document. This is pretty much all about the project, and thanks for watching.